Good evening, everybody. Welcome to tonight's edition of the Triangle Area SQL Server User Group's Advanced DBA session. So tonight we are going to learn about graph so data models and query patterns in Azure SQL. And we have with us a couple of outstanding people to talk to us about this particular solution in Shreya and Arvind. And with that, I'm just going to hand it right over to them.
Sounds good. I'll just introduce myself and then hand it to Shreya. Hey everyone, this is Arvind Shamsundar. Just call me Arvind. I'm with the product management team, part of the Azure SQL group within Microsoft. Glad to be here and talking to you. Shreya.
Thank you, Arvind, and thank you, Kevin. Hi, everyone. My name is Shreya Verma. I'm also part of the product management team along with Arvind in Azure SQL Database and owner for graph data modeling and SQLDB backups. And I'm also glad to be here today. And with that, we'll get started with our session today here. And we are going to, in this session, we are going to talk about the graph data models and query patterns that you can use in Azure SQL. So to begin with, I wanted to give you a quick, here we'll just look at the quick agenda that we are going to cover in the session today. And we are going to go over some relevance of graph, what is the relevance of graph databases and relevance of graph databases in the industry and in use cases. And what are the different Azure SQL Graph capabilities? And then there are some cool demos and customer scenarios that our business put together, which he will describe and go over. And during the presentation, at any point of time, if you have questions, please feel free to post them in the chat. And I think Kevin volunteered that he will bring those questions up with us. All right. So looking at relevance of graph, so I just wanted to start with what is a graph database first, just to level set and just to bring everyone on the same page. A graph database is nothing but a collection of nodes and edges. Nodes represent your entities and edges represent your relationships, just like a relational database where tables represent entities and foreign keys represent relationships. But then you'll ask, what is the difference? Why do you need this special type of a data processing model? So the difference here is that the edges or the relationship can easily represent many-to-many type of relationships, and they can flexibly connect any node to any other node in your graph database. Unlike foreign keys, which are usually one-to-many. And if you want to do many-to-many using foreign keys, you would do junction tables, and then using those junction tables, you would write multiple join queries, making your queries even more complex. So all those type of scenarios, it's easy to model using the edges or relationships in a graph database. And you can have like properties associated to both your nodes and edges in a graph database. So your nodes can have user-defined properties associated to them. Your edges can also have user-defined properties associated to them. For example, in a social network, if you have a likes edge, like a person likes something, some organization or some restaurant or another person, then this likes edge can also have attributes of its own, like when did they start liking it, so date, or how many stars do they give, that type of information you can store on the relationship also. And you can, usually the graph databases, the native graph databases would make, querying your graph or traversing your graph easier using a graph query language. Different vendors support different type of query language, Cypher or Gremlin, I don't know, like two popular query languages supported. They just make, graph traversal or multi-hop navigation or path traversal kind of queries easier to write. And graph databases support both OLTP and OLAP workloads, just like relational databases do. So where would you use a graph database? In which scenarios would you use a graph database? So when we started building graph database capabilities within SQL, we surveyed a lot of customers. And even now, after we have added these capabilities, there are some typical use cases which we see where customers use graph data models. And one of them is hierarchical or interconnected data. And hierarchical data can be easily represented in a relational database, and relational databases are known to support hierarchical data types for years now. But with increasing increasing data in applications and evolving application scenarios and evolving type of relationships in these data sets, we see that there are, a hierarchy is not just a typical parent-child hierarchy anymore. There could be complex relationships between different levels in a hierarchy, or the leaf nodes could be connected to each other. There could be multiple connections between these hierarchies. It's not just a straightforward parent-child relationship anymore. For example, here you can see that in an employee hierarchy, a person could have a manager, and they could also have a technical lead. So they could have two parents. And representing this type of data using hierarchy ID or hierarchy in hierarchical format in relational database can get tricky at sometimes and complex. So using a graph model for these type of data sets makes it easier. Other one is when your data set has complex many-to-many relationships. So I just briefly talked about it in the previous slide that foreign keys can be used to do one-to-many, but when you have many-to-many relationship, then it just gets more and more complex to model it using foreign keys and junction tables and whatnot. So modeling those many-to-many relationships just comes naturally to graph databases using the edge tables, which can flexibly connect any node to any other node. And third type is when you want to make inferences or non-obvious connections from the data which is available to you. One example that I often tell customers is a very simple scenario of product recommendation. When you go on Amazon.com or Walmart.com and you want to write queries like when you are buying a product, they show you at the bottom of the page product recommendations based on people who have bought this product have also bought these products. And so these recommendations are based on the simple logic of people who bought this have also bought this. There could be more data associated to it, like people living in this place who buy these type of products also buy these type of products, or climate affects certain products in certain way. So all these type of inferences when you want to make from the data set which is available to you, making those type of not easily visible data inferences, you can do that using the data model that is presented to you by graph databases. So graph databases make it easier analyzing that type of data. So we have seen some real world scenarios where people use graph databases, which I think Arvind is going to go in detail later on in this presentation. And some of them are like contact tracing, which is right now very relevant because of COVID pandemic. So for contact tracing, people are looking at they are using graph databases. There are CRM scenarios, this content management, which is typical hierarchy. And then, a personal search, which could be complex connections, many-to-many connections. And then there is some scenarios like energy grid data analysis. So very typical relational database scenarios, which are now being, customers are now starting to use graph databases for these type of scenarios also. So it's not just social network or, network of computers where graph databases are limited to now. These are other scenarios where they are being useful, and there are many more such scenarios. Now you would ask what are the typical graph database workloads. So graph database workloads are OLTP, like I mentioned before. There could be OLTP workload, point lookup queries. So you can have a person in your graph and you want to find out who all are friends with that person. So you're starting from a given person and you're trying to find all their connections. So things like that. A BI or aggregation query, where you have a big graph and you are trying to analyze, towards the end of the year, what was the total consumption of this particular product in my product graph, things like that, or average consumption, so queries like that. And then there are graph databases can also do a specific type of analytics called graph analytics or graph algorithms. And you might have heard things like shortest path, page rank, or community detection, or betweenness centrality. all these. So graph databases would usually give you these algorithms. Either they support out of the box or they support a query language using which you can write such functions. So now let's look at why we added these capabilities, graph capabilities to SQL. And what are the capabilities which are present in SQL Server or Azure SQL Database? So I want to start with why we initially added this to SQL. This is a question that I get quite a few times from customers, that SQL is a relational database. It's a relational engine. And why did we bring graph processing capabilities to this relational engine instead of building a new product altogether? Because there are quite a few native graph database products out in market. And why didn't we just create something like that, which is native and can do more native, graph database processing and store data in that format? So our reasoning was very simple. We wanted to embrace and extend. When we surveyed, like I mentioned, we surveyed quite a few customers before we started building these capabilities into SQL Server. And when we surveyed the customers, we realized that SQL Server and Azure SQL, both of them are very matured products. Relational database and SQL has 40+ years of academic and industry research behind it. And it has highly evolved ecosystem of users, of community, and tools and everything. Like it's a very evolved ecosystem. So if you build something with this, we get all of this out of the box. Then SQL Server is also a very trusted product by millions of customers for their enterprise and mission critical workloads. So building this into the product brings both the best of both relational and graph database to these customers. And now these customers do not have to take their data out of a relational database and put it into a graph database for graph processing or graph analytics. So, and they don't have to pay for 2 licenses for 2 different products. And by using one service, they are able to now process. They will be able to process both their relational data and their graph data. And SQL was already it is on-prem. It is available on cloud, and you can write hybrid applications with it. So you can have your part of your application running on-prem, part of your application running on cloud, and they can talk to each other, and you can develop your applications that way in a hybrid manner. And lastly, there was enough research which was backing the fact that graph database processing can be done within a relational engine, and that relational engines are matured and evolved enough to support, graph processing type queries in it. There was enough research showing that, so which gave us confidence that we can build a product like that, which can be used by our customers, and that will help them save, like I mentioned, the licensing costs for 2 different products, and ETL, expensive ETL operations. Now moving on to what are the capabilities in SQL, Azure SQL or SQL Server for graph. So like I said, a graph is a collection of nodes and edges. So you can now define a graph schema in SQL. You can create nodes and edges. And since we use the basic relational engine as our basic primary storage format, we created nodes and edges. We allow creating nodes and edges in form of tables. So you would create a node table to represent your entities and an edge table to represent your relationships. So to support this type of schema creation and navigation through graph or traversal through graph, there are obviously some DDL and DML extensions. So DDL extensions that allow you to create node and edge tables, and then query language extensions to allow you to traverse your graph. And we added a match built-in and shortest path built-in to allow you to traverse your graph or navigate your graph. And then tooling and ecosystem, like I mentioned before, all of tooling that you get with SQL Server, ecosystem that you get with SQL Server, it just is available to you when you use graph features. So things like SSMS, ADS, they just work out of the box. Things like security features, dynamic data masking, row-level security, or HA, high availability, or machine learning using R and Python. You can just use it with the graph features, just like you would use it with relational database tables. Now let's look at what are the DDL extensions and how you can create a node or edge table in SQL Graph. So creating a node table is very straightforward. You would create it's just like you're creating a regular table. After defining your table definition, you will just add as node in the end. This is a special syntax which tells the engine that this is a special type of table, and it is a node table. And all type of data types are supported, all type of indexes are supported, and all type of constraints are supported, including indexes, including clustered and non-clustered column store indexes. And what happens when you create a node table? What is happening behind the scenes? Why do we have to specify as node in the syntax? Why can't we just create a table and tell the engine that this is a graph table, right? So when you create a node table, behind the scenes, along with the user-defined columns that you have in your node table, we create an implicit column, which is called as $node_ID. And this is a unique identifier for each node in your database. And it is a combination of table name and internally generated sequence. When you select from the table, you'll see a JSON. However, it is stored as a big int on the disk, so it's not that big. The memory footprint is not that big. And we create an implicit unique index on this column, which later on helps us with faster navigation. So if you are creating a node table and if you define a unique index on this table while creating the table in this creatable definition, we don't create the implicit index. We only create it if the users have not created this index. So we don't duplicate the index, basically. Next, how would you create an edge? It looks just like creating a node. Instead of saying as node, you say as edge, which tells the engine that this is a relationship. Again, all data types, all constraints, all indexes, including column store and clustered, non-clustered column store indexes, clustered and non-clustered both, they are all supported. An edge table may or may not have a user-defined column. Like here in the friend of edge, we do not have a user-defined column. And when you create an edge table, along with the user-defined columns, just like in the node table, there was one column, which was $node_ID. Here we create three columns, which is $edge_ID, again, a unique identifier. Again, there is a unique index on this. If you do not create a unique index, we create one implicit unique index. It uniquely identifies each edge in the database. When you select, you see a JSON, but it's stored in form of a big int internally. It tells you what type of table this is and an internally generated sequence. And then two other columns, which is $from_ID and $to_ID, which tells when you insert data into an edge table, these columns tell which type of nodes this edge is connecting. So if you notice, when creating the table, we never specified which type of nodes this edge is going to connect. And only when you insert the data, you provide the node IDs of the nodes that this edge is connecting. What that means is an edge can flexibly connect any node to any other node in the database. What that means is that you can use a single edge to connect all your nodes with each other in the graph. However, we wouldn't recommend that because that would make your edge table super big. So we recommend that you create one edge table for per relationship type in your graph, and use those edge tables for the connections. Now, this was back in 2017 in the first release when we supported edge tables like this. Later in 2019, based on customer feedback, people wanted more better integrity constraints on edge tables. They didn't want an edge table to be, allowing everything. So we introduced a special type of constraint on edge tables, which is called connection constraint, which allows you to enforce, specific semantics on the edge table and also maintain data integrity. So what this edge constraint is doing is it's telling that the bot table can only connect a customer to a product. So you cannot accidentally insert an edge which will go from product to customer, because then that will mess up, your connection table. So it will fail that type of insert. If you try to insert anything else other than an edge which is going from a customer to a product, if anything else is inserted, that insert will fail. And on delete cascade here specifies what happens when a node connected to this edge is deleted. So for example, if this connection constraint was not there and you delete a person in a customer record in your database, and that customer may have bought several products over their life cycle in the database. And when you delete that node, all the edges going out from that customer to the products that they have purchased will stay there, dangling, and it's the onus is on the database developer to remove those dangling edges. But here with delete cascade, what we do is we delete those edges incoming or outgoing first, and then we delete more, so that there are no more dangling edges or dangling connections in the graph. Inserting into graph tables is quite straightforward. You like inserting into node table is very easy. You would insert just like you would insert into a regular table. Node ID is implicitly generated column, so you don't have to explicitly insert into that. Inserting into an edge, when you insert data there, you have to remember you must specify the values for from ID and to ID, because that is when you provide which nodes this given edge is going to connect. So for example, here in this, I'm trying to insert a bot edge, a bot relationship between a customer and a stock item. And I'm saying is create a bot edge between this particular customer with customer ID, this value, and this particular stock item because they've bought this stock item, and this is the purchase count of that. So I'm inserting the node ID from the customer node and node ID for stock item from the stock item node, and inserting those values here. Now looking at the query language extensions and match predicates that we added. It's a simple predicate that lets you go or traverse your graph. And you can use it in a select statement, and your select statement will just look like what it looks in your relational queries. You have a select, then you project the names that or the columns that you want to project or project out, and then in the from clause you have your table names, nodes, and edges that you are going to use for the traversal. And in the match clause here, you go from the one node to another node via an edge. So in this query, what I'm trying to do is I'm trying to find all the customers who have bought a stock item, and that stock item being all-purpose bike stand. And I want to get a list of all these customers. So I'm going from customers to stock items via the bot edge. The arrow here in the match clause represents the direction of the edge. So if you remember here, when we inserted into the bot edge, we in the previous slide, we said we are going from customer to stock item, right? From ID to ID was customer to stock item. So we were going from a customer to stock item, and that's what we are doing in our query here. We are going from a customer to a stock item via the bot edge. And you always go from a node to another node via an edge. You never go from a node to node directly. You always have to traverse via an edge. You can't go from node to node directly. Now there are a few features that we added which are very useful, which we added to SQL Graph, which are very useful in some of the scenarios typical to graph databases. One of them is view or derived table usage in match query. Now, if you have queries in your graph, in your database where you want to find, things like find me all connections that I have, all type of connections. For example, on LinkedIn, if you want to find everything that you like. So you could like a person, you could like an organization, you could like a group, or you could like an article. So how do you get that information? So for that, what you would do is you would find all the persons that I like, then you would find all the organizations that I like, then articles that I like, and then so on and so forth, and then join the data results together to find everything that I like. So to support that type of scenarios, so what we have done is we supported use of views or derived tables in the match clause. So what you would do is in the example here, I want to find all contact information for Alice. Now Alice has an address, she has a phone number, she has an SSN. So to find the complete or all contact info for Alice, what I have to do is I have to query her address, phone number, and SSN, and then join that data together and get the complete information. Instead of that, what I'm doing here is I am just pulling the relevant information from her address, from her phone number, and from her SSN, and I'm using the union all operator to combine them together. And I called it all contact info. This is a derived table, but I can also create a all contact info view by that name if I'm going to repeatedly use this type of this type of union in my queries. So I can create a view, and then in my match clause, what I say is start from a customer and find all their contact info, and my customer is Alice. So if I replace Alice here with Bob or David, I'll get contact info for Bob or David. So the view or derived tables can be used to support that type of queries. Find me anything that I like in graph, or find any connections that this particular node has in my graph. Next feature is shortest path. So we also introduced a function called shortest path in T-SQL, which can be used inside match. It works on graph nodes and edges, and the way this works is basically in my graph here, I want to find how Bob and Mark are connected to each other. Now there can be multiple routes in which Bob and Mark are connected, and we see multiple routes here in the picture. And I want to find only the shortest path. So this function here, it does that, and the way it works, it's basically just a simple implementation of Dijkstra's shortest path algorithm. It implements BFS internally, breadth-first search. What it does, it will start from Bob, and it will fan out. It will find first-level connections. If Mark is found in the first-level connections, we return Mark and we quit. If Mark is not found, we take the first-level connections, we fan out further, we find their basically second-level connections. If Mark is found there, we return Mark and we quit. We stop the recursion. If not, we keep going. So if you see here at the shortest path function, what it is doing is that it's starting from the from customer. The from customer here is Bob, and it says that traverse the friend's edge, because that's the connection between people in our graph here. Traverse the friend's edge and keep finding two customers, the next level, until you find Mark. So this filter here is telling until the last node is Mark, keep going. So now in this pattern here, the friend and the two customers, these two things are going to be repeated again and again. So they are basically a collection or a path object, which is going to be traversed again and again recursively or repeatedly. So here we put them inside these brackets and put a plus, which shows that keep traversing until you find the destination node, or quit as soon as you find the destination node. Now this plus will actually traverse the entire graph, so it's a very risky operator to use. Instead of that, inside curly braces, you can also use 1, n or 1n as in 1, 3 or 1, 5. So what that means is go until 5 hops, 3 hops or 5 hops, and return if you find Mark before that, or stop after 5 hops, because I don't want to keep recursing or repeating in my entire graph and run this query for a long time. So this is how, and because these friends and two customers is something that you are going to traverse again and again, this has a special meaning, and the way we tell engine that this has a special meaning is by using this for path syntax in the from clause. This tells the engine that these two entities will be repeated again and again in the query, in the shortest path query. And because they return a collection, instead of returning, the table rows, they return a collection of a friend and of an edge and a node. The way you return data out from these nodes and edges would be using aggregate functions, because they are returning you a window of aggregates. So you use aggregate functions, string ag, last value, sum, average, count, all of those are supported. Now looking at a simple, straightforward example of product recommendations that I was talking about earlier, that you have a customer, they have bought a stock item, then stock item was supplied by supplier, it was coming from a location, customer is also from a location, and then we have some social aspect here that customer is also friend of another customer. Now in this simple schema, if you want to implement the product recommendation query, this is straightforward schema, can be easily represented in a relational model. If you want to write a product recommendation query in the relational model, when the schema is represented in form of tables and foreign keys, that query will look like this. So you have your current user, then you find the item that they are purchasing right now. You take this item, then you go in your database and you find the other users who have purchased this item. once you have those other users, you find the other items that these other users have purchased. And once you finally have a list of other items, you make the final recommendation to all your current users saying that, okay, since you are buying this item, people who have bought this item have also bought these, these other items. That becomes your recommendation. Now, not very easy to write query and not very easy to extend or not very easy to maintain. Now let's see if this were to be implemented using the graph approach, how that query will look like. And that query, 56 lines of code, turns into 17 lines of code with graph implementation. And what we are doing here is we are trying to find all the customers who have bought this item that our current customer is buying. And then once we have a list of all the customers, we find a list of all the other items that these customers have bought. And that list becomes our recommended items. Right? And we filter out anything that our current customer may have bought from this list already or what they are buying right now. We filter out that. And then we return that list to our customer. So it becomes very easy, straightforward to implement. Now, if you were to extend this query, for example, if you wanted to find the suppliers who have supplied these recommended items, right? Now imagine extending that query here. Like it will be another city added, 2 or 3 cities added to this query. Will take some time for someone to implement and write it. But in graph implementation, that query will just become like this. You already have your recommended items query. All you do is you extend that query by adding more match match patterns to it. All you say is these recommended items should be supplied. Get me the list of suppliers who have supplied these recommended items. So recommended items are supplied by a supplier. So basically, the point is that the way you would imagine or you would whiteboard your query is the way you would write your query in your query language. So extending a query or implementing your queries could be very easy, very intuitive in the graph implementation. And with that, I'll hand it over to Arvind for some cool demos.
Sure. Do we just want to do a check on questions at this time?
Yeah, we've got a few questions in here. So the first one, let me check. All right, from Mike, is there any support in Azure Data Studio for graph functionality other than writing normal T-SQL statements?
Yeah, it was there. I think this question was more specific to graph visualizations, probably, if I understand correctly. And today we do not have any graph visualizations, data visualizations in Azure Data Studio or SSMS, but we are looking into how we can extend support and bring that support to Azure Data Studio.
All right, thank you. Are there best practices for data tagging nodes and node groups?
I'm not sure if I completely understand your question. Arvind, do you know about data tagging?
I don't want to assume anything about the question, but is it about labeling node types and so on? I think it would be helpful to elaborate, because in a strongly typed system like in SQL, because each table is like a formal type in itself, right? It's a formal object type and so on. The necessity to tag a node as a particular type and so on is not exactly needed. So I don't know. I think it would be easier to get clarity on the question again, and then hope, because there's not like a direct concept of a node type, or I mean, other than the table is itself a type, so, in that sense.
Raymond, you're on the clock. Next question, while we're getting clarification on that, are there any suggestions for performing joins on quite disparate data sets? So, for example, looking at logistics and parts, tracking activities against events in a notebook.
I'm not sure if I understand that question also completely, but could you repeat that question, Kevin, one more time, please?
Yeah. Are there suggestions for performing joins on very disparate data sets, like logistics and parts? So I think what the question is, and again, feel free, chat, to correct me if I'm wrong. Thinking about how you have a parts catalog and maybe you have a lot of different parts items in the catalog, but you may not have that many um, uh, pieces of information about what's in transit, what's in storage, what's in a distribution center. So
How do you represent that in Graph? Or how do you query that in Graph?
yes, perhaps so. I think that one also needs clarification.
Yeah, and maybe if we go through some of the, there's a couple of
Scenarios,
examples that we have of data models and use cases. Maybe that question might be
yeah,
easier to answer, but we can wait for clarification as well.
yeah. Yeah, I think Arvind has a lot of scenarios, different type of scenarios that he's going to cover, which hopefully will help answer questions like this.
Yeah. So while we're getting clarity on those questions,
Okay.
next one is, do you have any thoughts on, say, rough practical limits on data sizes when it comes to number of edges or number of nodes?
Yeah, that's a good question, and that we can answer. Yeah, no, there are no limits. The size of data or the number of attributes you can have on your node or edge table, or the number of rows you can have. That is like all the limits that apply on a relational table. Same limits apply. So the number of columns. I can't remember how many columns you can have in a table, but those limits apply. And the number of rows, again, it depends on how big your database is, and there is no actually size limit on that.
Yeah, the largest graph that we have in our internal systems, at least for test purposes, is 128 billion edges, and if I remember correctly, that particular graph has close to 3 billion nodes. There are other graphs which have more nodes and somewhat lesser edges as well. So, and these are all like real world data sets. So the ability to handle size-wise, I think data size-wise, we are very confident about the ability of SQL to do the job. And the rest of the limits apply as per the engine, right? So as Shreya already clarified.
Yeah.
Sure.
Yeah, and again, like for querying, for faster querying, like I said before when I was explaining, you can create all the indexes, so for traversal or for read scenarios, creating indexes on your node and edge tables will also help. So with that much amount of data, obviously that Arvind mentioned, we do have indexes defined on those, which help with faster traversal. But it works. We don't have any concerns with the amount of data.
Okay, thank you. So it looks like no more questions at the moment. If we get clarification on those two, then I can ask them again in a little bit.
Okay, I guess we can move on then.
Yeah.
Let's see if, yep, I think, yeah, Shreya can, thanks for that. So what we thought we'll do is in the second half of this talk is to kind of look at some scenarios and to make it a little easier to understand both from a practical example point of view and from a real world use case point of view. What we're going to do in the next couple of minutes is to interleave some synthetic examples in the form of a neutral demo data set with a suffixed sort of a simulated or a redacted version of a real world customer use case. So that way we thought it would be easier to first of all see something in action, but also correlate it to certain use cases that we have actually seen customers using these constructs in. To make this a little bit more easy to visualize and to see things in action, we decided to use a fairly well-known uh, synthetic graph data model and associated data set, which comes from the Linked Database Council. So that's what LDB stands for, and the LDBC just stands for Linked Database Council. So they're a consortium of various researchers and industry um, representatives who work on creating a standard, a benchmark of sorts for database for graph databases. And one such benchmark that they have developed is this thing called the social network benchmark. So the social network benchmark is SNB, that's the acronym here, and it's a very kind of simple model. If you think about it, it's kind of like your typical social network uh, type situation. But the beautiful thing about that particular data model is that it allows the expression of many query patterns that are applicable to real world use cases. So this data model is while conceptually simple, is pretty complicated in the sense there are lots of objects in there. So I don't want to get into each one of these objects here, but I will summarize and then we'll move on to see some demos in action. The LDBC sort of data model is split into two broad halves. So there's some static data and then there's some dynamic data. So consider static items as things which are relatively, kind of constant. So things like countries belonging to cities belonging to particular countries and so on, or universities and organizations located in a particular place, so on and so forth. So stuff that doesn't change that frequently. On the other side, you have dynamic data, which is, in a social network type scenario or a professional network type scenario, you have people, you have forums that they interact on, and associated objects that they post in a forum. So, for example, posts and comments are objects that they would create or interact with in a forum. There's also the relationships between people. So persons knowing persons, and persons being moderators of certain forums, persons posting certain posts or comments, so on and so forth. So there are a lot of relationships or edges in the context of a graph database. This, as I said, the schema on first glance might look very complicated, but there are a few things that we're going to focus on just to kind of synthesize some query patterns. One of the things I want to just call out at this stage is recall what Shreya mentioned about virtual tables or views, or cases where you have a sort of a union all type query, which is composed of two distinct graph tables, and then you have a view on top of those. We're going to use one of those, in our example here. So we're going to have a virtual, so message is kind of like a base class, if you may, in a programming kind of a paradigm. And both posts and comments are modeled as individual graph tables in our case, and they roll up into this virtual thing called a message, which helps demonstrate this polymorphism in action, right? You have two different things which are actually the same thing, which is like a message, and you want to operate on messages all at one go. We are also going to explore the relationship of people to other people. So notice that there's a circular relationship here. So people knowing other people can be a many-to-many relationship, obviously. So we're going to focus on that in some of the queries that we run later. The other things that we will try to extract is that people might have one or more contact details. So just like Shreya mentioned, they may have more than one email address to deal with. They may have attended one or more universities, or zero or more universities, depending on their backgrounds. So keep these in mind. There are a lot of relationships which are optional, but they're kind of like aggregate in nature. So for a person, I might want to know in a single query all of their email addresses and so on. So there's some characteristics which we will find are quite interesting. So again, this is the more you peel this apart, this data model can get really complicated. But at the core, remember the big ticket items, which are there's some static items, there's some dynamic items, and there's plenty of relationships between those. The LDBC spec is available online, just for the record. I have a link to it in the slides that come up. And the LDBC spec it talks about certain interesting queries that you can run on top of the model. I'm going to show you the queries that we selected for easy demonstration of some of these concepts. But obviously, there is a data model as well, which is in the form of graph tables. So I'm going to very briefly show you that in action as well. But to do this more, kind of interactively, what we thought was show you a synthetic demo based on the LDBC examples, and then try to explain why is this pattern of queries important and correlated to some real-world customer examples. So that'll follow in a minute after we show you this synthetic example first. So one of the queries that the LDBC spec, for example, defines is what we call as a fairly straightforward query, which is you have a person, all right? You have a person of interest, and that person knows other people. So the person knows another person. So this is an edge, knows. The person of interest being here, they have friends. So that's the friend context of the person table again. And that friend posts messages, and you want to filter those messages for a particular date range, and try to kind of find recent messages that that all the friends of a person have posted, right? So a fairly straightforward looking query, and you could very well have a traditional like a join based approach to implement this. But let's take a look at what it would look like if we had to implement this using graph constructs. So I'm going to switch and kind of open up Management Studio, because that is still my personal choice for for coding and querying SQL. You can very well use Azure Data Studio as well. It's a matter of principle or personal choice. So my choice is to use SSMS for now. So again, recall the scenario is you want to know, given a person, who are their friends, or who list their friends, and for each of those friends kind of enumerate the messages that they've posted in the last 20 days. So in this case, we picked some hard-coded dates just for simplicity, and we're saying, hey, kind of filter. All right, let me step back. Let's break this down a little bit. So what are the objects that we are dealing with here? So we have a person table, which is the object that you saw, which has the person, entities in the database. You have this virtual object, which is called a message object, which is a view. The view looks like this. So if I if I go to the right definition here, the view in our case is actually composed of a union all, just like Shreya showed you. It's composed of a union between the post table, which is like the first post in a, like the first message in a thread, and then comments to that post. So these are typically replies to the post and so on. Posts have certain subset of the attributes that, comments have a subset of the attributes that a post might have. So for example, comments do not have an image file in this particular synthetic demo. They do not also have a language specified, unlike a post and so on. So what we chose to do is create a superset, which is this sort of derived object, which is called a message object. So we're going to probe for messages, which means we are going to probe for both posts and comments. So we are leveraging this polymorphism capability that SQL Graph allows you to work with. And we're going to use an edge, which is called has creator edge. So message has a creator, which is a person. And in between, we also need to navigate from the person to their friends. So we have to use an edge called knows. So we have two edges and essentially three nodes or three instances of the node. which is this 2 occurrences of the person and 1 occurrence of the virtual node type, which is called message. And obviously, as we said, you could potentially have implemented this query using like a traditional join approach, but just take a look at the match predicate here. And of course, opinions could vary, but in my mind, it's a lot more easy to understand what are we trying to do here. So we are trying to say, find me messages who have a particular creator, which is this alias f. And we also want to know direct friends of a person. So we're saying P knows F. So that's the way you read this. It goes from right to left. And this particular piece of the predicate goes from left to right. You could have very well combined this expression into a compound one, which would look something like this. So you could have taken this off and you could have said, hey, I want to know who are my friends. So that's this piece. And I want to know the messages that they've posted. So both these approaches would work. For simplicity, I chose to break up the compound predicate using an and. But as I said, you could have that bidirectional arrow coming in to make it even more elegant, if you may. And then it's all just T-SQL, right? So you're just filtering by the person of interest, this date range, as we mentioned, and then you project out the return values that you are interested in. So a query like this is pretty quick to run because it's not recursing through the graph. It's just a one hop between the person and their immediate friends. And from that point onwards, once you know the friends, it's another hop to get to the messages that those people have posted. So it's a fairly straightforward query and comes back relatively quickly. A lot of the traditional T-SQL constructs are at play, and the most important change or addition is the match predicate that we have here. All right. So I want to pause if there's any questions on this, because this is kind of like level 100 type query, and just make sure there's any questions which we can take at this point in time.
Yeah, let's see if there are any questions here. So there is about a 20-second delay between when you say something and when the world hears it. So that short stream delay means that people may not be typing just yet, which is why I'm vamping for a little bit to see if there's anybody who's going to be typing anything in.
Okay, sounds good.
But so far, so good.
Mm-hmm. All right. So that was like, the first synthetic demo. So just to recap, we took a person, we took a person that's here. We found their friends, and then we found out which messages they have created, wherein the friends are the creator of those messages, and we implemented predicates and so on. So where is this kind of a query used, or what are the typical scenarios where we might have observed this query pattern of simple predicates being used by actual customers? One example that again, there could be plenty of others, but one recent, relatively recent example is this, scenario of contact tracing for exposure to the virus, for example. And there are two, approaches that are generally accepted in the industry. The one that we've been kind of seeing is relatively more common for our purposes is this thing called forward only or prospective tracing, which is you take a person, you find out the persons whom have the virus, typically due to a positive test or something, and then you have typically these people would have a contact tracing app or something that they were carrying, and that would allow the provider or the health authority to know where they went. It could also be in certain closed scenarios, like in an industrial setting, or in like specific sectors like travel or so on and so forth, where exactly where people are at a particular point in time. So a very simple graph model for this would be to represent people and place. and you have a similar overlap to what we showed you in the LDBC example, and you have attributes like if the people if a person visited a place at a particular point in time, when did they exit that place as well? So you have begin time, end time kind of attributes, and it's very simple then to implement a simple forward only type tracing. So again, this is an example that we can kind of show you. It's again a mock-up of a real-world type application where a simple, you've identified a person called person one whom you know have had the virus, and you want to go back in time and try to find out where they were at particular points in time. And you have time intervals which are depicted as epochs, in this case, like a timestamp type field. And it's relatively easy to express the intent of your query using this match expression. And I think that's the key thing that I want to kind of reinforce. What Shreya showed you earlier, where you had those 50-odd lines of code and then less than 20 lines of code, is not something abnormal. In many cases, we see this kind of very elegant expression of intent being possible by using the match predicate. All right, and rest of this is just traditional T-SQL predicate. So that's the power of both. You blend this ASCII-art sort of cipher-like syntax with traditional T-SQL syntax. So that's example one. I'm going to show you another example, and then we'll again pause for questions where we can take some time to answer those. The second kind of pattern that we see is a little bit more complicated than the first one, where the first one was simple, kind of like you have one hop, and then you have another hop, and then you filter. The second pattern we see is recursive querying. So this is where we introduce the shortest path construct that Shreya had mentioned early on. And to do this, I thought it would be easiest to use a traditional hierarchy type situation. The LDBC spec that we kind of use for this a lot of these demos has a lot of recursive queries. I took a very sort of abridged version of one of those, which is let's say we have a city in the data model for the graph. I want to find out which country it rolls up into, and possibly higher. So this would recurse back to the continent or something that the country is contained in. And this kind of a query, again, as Shreya mentioned, you could have implemented using CTEs and the hierarchy ID data type, for example. But in a T-SQL graph query world, it's fairly easy to implement it once you get the hang of the shortest path expression. So in the screen, in this query, what I have here is the intent of my query is to find out the city called Delhi, capital of my home country, India. Um, where does it, kind of ascend into? What's the hierarchy that it kind of ascends into? And the way you do this is in the LDBC graph data model, we have a relationship or edge called is part of. So, and is part of edge connects place to place. So it's like a circular thing, but it's very useful to navigate this kind of a hierarchy. So the query is broken down into the following. In the from clause, we define place twice, because again, recall this is a circular relationship. So we say, hey, I want to go from a place which I define as a child alias, and another place which is a parent of this child, and that's linked through this edge called is part of. Now, given this is recursive, or I want it to be recursive, I have to declare the modifiers as for path, as Shreya briefly mentioned. So for path basically says that you're specifying a recursive query. So is part of and the parent are both considered part of this recursion, if you may. And it's upwards in this case. We are sending the hierarchy. And the way you define, so if you compare this with the old short, I mean, the first match expression, the first match expression didn't have an embedded shortest path specifier. So in this case, we're saying we do want a shortest path between the child, and this is the recursive piece, which Shreya explained in one of the slides, saying, hey, recurse this traversal of getting to the immediate parent as long as you can. And because I could have, you know, the way recursion works in a graph is it looks for all connected paths. So the way shortest path works, as Shreya mentioned, is it's BFS, which is breadth first search. And breadth first search will allow you to reach multiple nodes. It'll do so avoiding loops in the process. So in this case, there's two things that we can potentially get back from this query. So I want to show you the inner query first. We'll run this, and you'll see that it comes back relatively quickly. And it says that India, in this case, it says it's part of India, which is, Delhi. Excuse me. It says Delhi is part of India, which is fine. We kind of know that. And then it says it's also part of Asia because it's ascended one more level. As you can see, it says this is the first level of climbing the hierarchy, if you may, and this is the next level. And it says, oh, we traversed through India, we went to Asia now. So the last node, which is kind of like the top level parent in each case, is pulled out by using this function called last value. I think Shreya briefly mentioned this, and it's there's a couple of these kind of window aggregate type functions that we can apply. And typically, you'll tend to use last value a lot if you're going to be doing these kind of recursive queries, because you want to know what is the end of the search. And then you also have something called string ag, which is just the traditional T-SQL string aggregation, which allows us to concatenate the path that we navigated to get to that particular endpoint. And the count aggregate, everyone is familiar with this, and that allows us to get the levels that we traversed to get to the hierarchy. So this is kind of the simplest possible recursive query that you could envision in a hierarchy type situation. Now, notice I said there's two levels that we could run this with. Sorry. So the first part was just to get all these ancestors, if you may. But I also want to get just the top level ancestor. So I want to see how far can I go up in the chain. And you can do that by having an outer query, which would filter and say, hey, let's order by level descending. So get me the topmost ancestor, if you may, for this particular child, which is this city called Delhi, right? So it's a fairly simple way to understand recursive queries. Recursive queries are not for hierarchy only. They are for traversing through the graph, and that's the beautiful thing about shortest path. You can apply it in any graph, and a tree or a forest of trees could be regarded as special cases of graphs, if you may. All right, so this is pattern number 2, if you may. It's one example of a so-called complicated query. And we find this in use, as Shreya mentioned briefly in the beginning, very commonly found in content management type use cases, where you have folders and documents within the folder. You have tags, or you have sort of comments associated with each of these documents, and so on and so forth. So that's very, very common use for these kind of recursive hierarchical queries. And you can use, as we saw in the synthetic demo, you can use it to answer a lot of questions, like saying, who are the parents who refer to this particular object in the case of a document, for example. I'm going to do one more complicated query and then stop for questions. This comes right out of the spec. This is probably one of the most complicated queries in the LDBC specification. And it uses a lot of elements which are a little bit mind-boggling to start with. So let's, if you read this, you probably won't understand it. So I'm just going to try to explain it to begin with. The objective of this particular query, synthetic query, is to start with a particular person. So again, I'm going to use this little laser pointer to make it easier. So we start with a person of interest. We want to know from that person, we want to know friends and friends of friends. So you're doing one or two hops. You want to know who are that person's friends or friends of friends, so 2 levels removed. And for each of those people, you want to know what messages they have created. Again, notice we are using message, which is this virtual table composed of those 2 post and comment tables. We want to know which messages they have created in a particular range of time. Also, we want to filter only for messages that those people created when they were traveling to a particular country. So this may appear very convoluted, but I think it's a very realistic example for some of the use cases that we've seen in real world applications of graph. So these people who are your friends or friends of friends, they travel and they post messages when they're traveling. And you want to know which of your friends has posted messages when they were traveling to 2 specific countries. So in this case, it's a combination of recursion, which is here, and traditional like filtering type stuff. But in the process of filtering, you also have to explore and traverse this edge, which is the edge between people and or persons and messages. And you also have other attributes that are to be filtered on based on the name of the country that they visited and so on. So this is a fairly complicated query. Let me rewind to that slide and go and show you the example T-SQL implementation. All right, this is a big query, so kind of take a deep breath, if you may. So for this query example, I chose to use 2 countries of interest. So we're going to see, given a particular person, so we start from here, a person identified by an integer, whose friends have, or friends of friends, have visited both of these countries. So you're looking for people who are friends or friends of a person and have been to Portugal and to Israel in a particular time span and also posted messages in that time span. So it's a lot of criteria that you're trying to combine, and it gets a little kind of gnarly, but it's pretty straightforward at the end of the day when you look at implementation. So the implementation can be a little overwhelming to begin with, so I'm going to try to break it down for you. The easiest way to go about this kind of a traversal is to start with the people to people or the person to person traversal. So remember, we want to find friends or friends of friends. So that's a hop length of 1 or 2. We do this by using the match combined with the shortest path intrinsic, as we already saw briefly. And this time, instead of specifying an unbounded traversal, like we just did the plus in the previous example, which is saying infinite or unbounded, this one says up to 2 paths or up to 2 hops. And here, the new construct that we are introducing is this thing called last node. We saw last value last time around, but last node is very, very important. If you're dealing with recursive queries, imagine the scenario where you found a friend or a friend of friends, and you want to latch on to that particular person and then explore from that point onwards which messages that person has created, correct? Which is our requirement here. To do that in a recursive query, you have to use this thing called a last node function. So last node says, hey, which friend am I talking about? So you're talking about the person that you've located through that recursive search. And then using the last node, which is the recursively found person, you can find messages that have that person as the creator. So that way you can find out which messages has this person created. And then once you locate the messages, because the message in our data model, in this graph model, the message has an attribute called the place ID, which is the country identifier where they have posted that message. So because that is a 1:1 relationship, so a message can only be attributed to one location, so it can't be in multiple locations. So we chose to implement that as a embedded key, if you may. And then traditional filtering applies as well. So it says, oh, I'm only interested in messages within a particular time frame and so on. So the most important twist on the tail in this example is the chaining, right? So the chaining of the recursive piece of the query using the last node function to other match operations. So this is very powerful, and it's almost an essential tool in your toolbox if you're working with large, complicated recursive queries. All right. And once we have this basic construct in place, it's just a question of doing traditional group by type stuff and filtering out the query to only operate on the countries of interest. So we said we I have to clarify one thing. So when I said Portugal and Israel, I think the spec says the person should not have visited those two countries. I got that wrong initially. Sorry for that. So that's why the filter here says that person that you found, the friend that you found, has not visited or has not posted those messages in either of these two countries. So small subtle clarification there. But in the end of the day, this query might look intimidating, but it's very performant to run with. And it says, I have one friend who is related to the person of interest who's been to these two countries, and this is the count that this is the count of messages that they have posted in those respective countries. And the deal is that, again, I'm trying to remember the exact criteria. The exact criteria is the friend should not be already located in that country. So they post messages in Portugal or they post messages in Israel, but they shouldn't be homed in that country. That means they visited the country. All right. So small, subtle things, but too much detail there. Hopefully you get the point. The most important thing is to kind of recall from this slide is the last node thing. Okay. So there was a lot in that. I think that was the most complicated query that I have to show for you today. But I do have a few more examples. I'm going to pause for questions and see if there's anything we can answer now.
Yeah, the first question is, how many records were being traversed in that last example?
In this one, I think we have around 8,000 persons in this sample data set, and messages, I think, number close to 800,000. And we filter those for a specific date range and so on. So in the end of the day, given a person, you're looking at upwards of hundreds of friends that you're potentially going to be traversing. So it's a reasonably large traversal.
Okay. And is it possible to see execution plans and live statistics for these queries like traditional
Yep.
T-SQL?
Sure, you can. I don't want to get too deep into that right now, but you can definitely use any and all traditional T-SQL tooling that you are familiar with. So just query plans would look the same. In this case, the recursive queries, you will typically see a lot more complicated query plan. And again, without getting into too many of the nuts and bolts here, because that is probably a session in itself, um, the key thing I want to emphasize is that you'll see some evidence of tempdb usage and temporary tables being created which have a name prefix REC, and that REC stands for recursion. But yes, you can use any and all traditional T-SQL and SQL troubleshooting and tuning tools. Indexes play a hand. uh, one of the standard recommendations we make is on all edge tables. Uh, we strongly recommend for optimal performance creating an extra non-clustered index on a combination of the $to ID and the $from ID columns. So short answer, yes, you can use a lot of the goodness that SQL has already.
Okay. And if I have multiple shortest paths, is there a way I can see all of them?
Not yet. It is one of our roadmap items to address, wherein the currently, if you have multiple shortest paths, and that means you have multiple paths to the same destination of the same length, we will return to you any one of them, and it's kind of non-deterministic. So if you want to have a deterministic return, you'll you'll have to have some other criteria there. But it is one of our roadmap items to have like an all shortest paths extension.
All right, thank you.
Okay, and for requirements like that, I think there are a lot of workarounds that we can apply, wherein we can, work with you to kind of implement a custom T-SQL approach to obtaining all the shortest paths. We also have examples for weighted shortest path that Shreya has implemented. So there's plenty of ways to use the match intrinsic and then still accomplish some of these extra requirements that we have. All right, so I'll move on. So a couple of real world cases again, where this kind of a complicated pattern, we've seen cases where there's access control type systems, where you again have a recursion element to it. And you have lots of complicated criteria to apply, like ACLs, right? So you have ACLs, access control lists, and you have a lot of complicated combinations of recursive search and complicated filtering as well. All right. The third kind of scenario I'll briefly talk about, because we've kind of explored a lot of this already, is pathfinding. And pathfinding being very, very common, we've already kind of seen this in action. So I'll very briefly touch upon what's different here from the previous query. So the previous query again looks similar, where you say, I want to traverse from a person to their friends or friends of friends, or a third level, increased this time. So you see if it goes from 1 to 3. And for each of these people that you locate in your friend network, you want to pull out other details like their location and a list of their universities. So university, you may attend one, you may attend multiple universities, you may attend none. Similarly, you may have contact details that you are associated with, and so on. This is an example of a recursive query with some aggregate operations on top, specifically for things like the university names that you have attended and so on. So I'm going to very briefly show this to you, and at some point we will get to posting these out in GitHub repo. But I'm going to summarize this for you for now, because this is a daunting query if you just look at it for the first time. The key thing here again is the recursive query, right? So we start with person and try to find out their friends who are either 1, 2, or 3 hops away. Once you locate a person of interest in the network, you chain that predicate and you say last node is located in place, because we need to know where that person is located. Once we locate their place, we then chain it upwards to find out, other details about that person. So where did they work at? And because the specification of this query demands that you have a single field in the output, so it's a single scalar, output. And there's multiple ways, obviously, to do that. In this case, I chose to implement it using a nested kind of a subquery, or a scalar subquery in this case. You could do it a lot more, elegantly. I'm sure there's more efficient ways of doing this, but you'll see the pattern applied to organizations that that friend worked at, universities that the person attended, languages that the person speaks, and emails that the friend might have in their records. So this is an example of combining a recursive search with a top-level aggregation of other related fields and attributes. So slightly convoluted, but somewhat realistic query again. And again, just to emphasize, the last node, the ability to chain these searches is so critical and useful. So again, this is going to run relatively quickly. Peter is the name that I have chosen to filter those results by. So again, you'll see a lot of the traditional filtering attributes, filtering based on attributes and so on is applied here as well. Devil's in the details. You can take a look at these queries. I think we will post them up. I think we can share them with this group. somewhat privately because we still don't have these finished up in a way that we can kind of confidently publish them publicly. But we'll make sure we get these out to you sooner than later. To kind of wind up, we have kind of like a real world use case where this kind of a chaining, recursive search chaining with other related queries is used. We actually have a published case study for a customer of ours, BKW Energy. They are energy, a major energy producer, and they have, they actually use Azure SQL um, and the graph features therein to do some pretty complicated queries between like producers and consumers, right? So you have grids in between, and you want to find out if there's an upstream event of some sort, like a power producer station is out, which are the related consumers who are affected. Can I redirect energy to those affected consumers from some other places and so on? There are lots of other cases which you can kind of see these complicated recursive queries at play. Again, interest of time, just being brief about this, there's a case study that we published for CRM, which is our own product, the Microsoft Dynamics CRM. They use this for like opportunity management and other cases. And another third use case, again, all of these are not just some great, kind of cooked up ideas. These are all redacted, simplified versions of real world customer applications where they're using SQL Graph. So here's a simplified example of a company that does personnel search. So like high-end hiring, think LinkedIn, right? So if you think about LinkedIn and recruiter looking for interesting candidates to approach and so on. So lots of applications where Graph and specifically SQL Graph is being used in today's world. The last but not the least, you can do some graph analytics on the data at rest in SQL itself. One popular thing is to be able to find influences in a network. For this, we chose to implement something called PageRank. There are other measures of centrality and so on that you can apply to find out more influential people in a network. But you could just do PageRank. I'll be very brief about this, but because again, analytics could be a subject in itself. But PageRank is essentially an iterative algorithm that we applied here. And what this does is it uses the match operator to try to traverse through the network. And PageRank being, what Google originally kind of applied to ranking web pages, is a fairly, useful way to establish which nodes in a graph are kind of central and more important. This being an iterative algorithm takes a little while. Again, this network of people is around 8,000 persons. It's not terribly big, but it's not a small network by any means. The output of this PageRank operation is a list of people along with their measures of kind of importance, if you may. So you could use this again. This being SQL, you could take the values that are output. You could update a parent table with the weights that are output by PageRank, or you could create a new derived table. In this case, this is just temporary table that we created with the output of PageRank. But you can do a lot of stuff that you're familiar with in SQL, and that's one of the beautiful things with having those graph capabilities in the core SQL product is you can do everything in one place without having to move your data out of SQL. And again, this is probably a subject in itself, visualization of graphs. I'm going to go very brief and very quickly through this, but again, this is like we could spend just hours talking about visualization. So this is what we've seen and what we've kind of used as input from customers. So when it comes to visualization, we typically find that customers want to view a subgraph, a subset of the nodes and the edges in the graph. and they typically want to see it in the context of some other application, some other front end apps stack that they already have in operation. Some cases they want to see a static picture. Some cases they want to see a dynamic, move and drag and drop type interface. So we've seen all kinds of a breadth of requirements from customers when it comes to visualization, which is perhaps one of the reasons why we don't yet have a standardized out of the box option. That said, again, as Shreya mentioned, it is one of the topmost priority items in our roadmap. We have some people working on it. There's obviously a feasibility and timeline aspect to it, but it is one of the most important items that we're working on from a feature point of view. That said, there are plenty of options available to you. Again, these are just examples of what customers have chosen to implement in their real world application. So we're kind of synthesizing it and demonstrating in a neutral way. Uh, Power BI being a first-party tool of choice for many Microsoft customers, we find is used quite a bit. There are two controls or plugins that are used. One is a relatively well-known and older one, which is this force-directed plugin, allows you to manipulate these nodes, kind of drag and drop them. A more recent one, which Shreya has kind of seen in action, is this thing called the Network Navigator. Again, this allows you to filter data, allows you to move nodes around and kind of see the dynamic visualization in action. A couple of community examples. This is from Lewis Davidson, who's one of our MVPs. He did some great work recently, using this format called TGF. And here's a sample visualization from one of his blog posts. I think a pretty neat implementation, very clean way of representing nodes and edges. Um, this is a visualization from some work that some of our colleagues are doing on certain AI type use cases where they're taking text data. And in their context, it's a different domain. But in this screenshot, what you're seeing is data from Stack Exchange, just to kind of illustrate a point. So a graph which is used to illustrate the co-occurrence of two words is very useful for deriving some kind of knowledge understanding. This would be the basis for a very preliminary knowledge graph, as they say. So visualization in this case that our colleague built was to use a third-party library called Viz.js. You have links to the library there. It's all JavaScript. It takes JSON data. So what he does is he pulls out data from SQL using like Node.js code, gets JSON output, and that JSON output is passed into this Viz.js visualization library. All of this is dynamic, though obviously this is just a static screenshot for now. So you can actually use the same drag and drop type feel for the nodes. A couple of other examples, you have plenty of options. Again, these are two examples that I have blogged about in the past. One is to use GraphViz. GraphViz is very, very well known in the Python and in the research world, useful for visualizing a lot of static graphs. Another example, which I posted a couple of years ago, uses a third-party tool, open source tool called Cytoscape. Cytoscape is well regarded by network researchers. So if you have a network or a social or a complicated network analysis type use case, Cytoscape is one of those highly regarded tools. And again, the best thing about Cytoscape is it has front-end JavaScript libraries, so you can embed that in your app as well. So there's plenty of examples. The key point being visualization, the ability for SQL to integrate within a broader app is what customers look for, and then they get data out of SQL in whatever form. Like it could be raw JSON, it could be proprietary formats, it could be open formats like the TGF or GraphViz. Once that data is obtained in the format that the visualization tool needs it to be in, it's relatively easy to allow like a JavaScript library, for example, to render the graph. All right, that was a whirlwind, tour of like visualization options. I'm going to pause for questions, and then I think we can have a wrap up from Shreya.
All right. If there are any questions for anybody from chat, now is a wonderful time to put them in right now. Is anything planned by way of visualization within SQL Server itself?
There are plans. We will reveal them as soon as we can. Shreya, you probably want to comment on this as well.
Yeah, like Arvind said, there are definitely plans. There are definitely visualization related things on roadmap, and he also mentioned that it is like our top priority. But yeah, we don't have a timeline that we can share yet. So whenever they are ready, we will be happy to share those details.
Yeah, it makes sense. If anybody has additional questions, are there best practices for? Okay, so yeah, best practices for data tagging nodes and nodes group besides indexing fields for processing.
Again, that could mean a lot of things. So I'm trying to visualize. So I'm guessing based on what was just mentioned about indexing, it's a unique way of identifying the node. The most common way that we would see, as you would have probably kind of got the gist looking at those demos, is to use attributes. So like fields, right? Columns. And you could have traditional, like, char integer type columns. You could also have a JSON, embedded JSON object within one of the text fields, and then use like you could either have a computed column to extract portion of the JSON. You could index the JSON using full text search. There's plenty of options. So honestly, I think it would be easiest to like take a specific example and work through it. But the most common way that we've seen is use attributes like properties in the graph. So it would be typically a column that represents that that criteria that you want to locate a node or an edge by.
All right. And it sounds like you were right about tagging being identifying. So it sounds like that answered the question.
Okay, sounds good. All right, I will hand it to Shreya to kind of take us through the last couple of summarizing and kind of wrapping up. Did Shreya drop off?
Looks like
Okay. All right. Let me do this real quick. So I will do the needful to wrap things up. Let's see if she joins back. Okay. I don't think maybe some IT issues. All right. So in closing, I think the main things we wanted to emphasize in this, kind of fast-paced talk was there's plenty of use cases that we see where graph models are applied and are in real-world use. You saw some of them. We tried to show you like a synthetic view of those, and also a bridge, versions of how real-world use cases are using those query patterns. Um, many times we get asked this question of relational versus graph, and for us it's the same thing. In the end of the day, we view the ecosystem as first class support for graph queries and constructs within the relational database itself. So for us it is a relational and graph solution, not a versus solution. So this is one of the key reasons why we have had customers move to SQL Graph from competitor products, and they found that the systems of record were different from those so-called competitor products, and in the end of the day, SQL provides them a way to have a single store combining security, HA, all the other goodness that you're familiar with, and familiarity with the T-SQL language footprint as well. And last but not the least, we kind of summarized very quickly at the end the breadth of options that we have from a visualization viewpoint. That topic is so big. I mean, there's entire conferences. If you look for Springer, Springer publishes like these thick tomes of graph visualization material, and it's a world in itself. So we choose to keep things quite neutral for now, but we are working on, as we said, tools of choice within the product. Most likely, Azure Data Studio is probably where we'll start seeing some of those options land in the future. And at the same time, if you really want to pull your data out for some advanced analytics, you can always do that using ODBC support from Python or a Spark connector that we have today. Shreya's back. Shreya, I was just trying to like wrap up. If you want to comment anything else on this, I kind of summarized
Oh, no,
briefly.
thank you. Thank you. Yeah, just one comment that yeah, we've seen many people use graph database for many real world scenarios, which you would otherwise think are very typical relational database scenarios. And they are not, these days, they are not just limited to, social networks or typical network analysis kind of scenarios. People are using them in all sort of fields and for all sort of use cases.
We'll make the slide deck available to you, Kevin and Mala, so you can, I don't know, post it somewhere where people can grab it. We have a lot of examples on GitHub. There's product samples which are in the Microsoft organization repos. There's a couple of examples that we have on the Azure samples, like my million song dataset is one of the first demos that we did way back in the SQL 2017 timeframe. Since then, I think the Yelp dataset demo is a rich one that Shreya has recently used in another event last week as well. It's probably the most illustrative of the power of like everything in the database. So you can do full text, you can do spatial, you can do graph, everything in one place. And in terms of size, there was a question early on. We mentioned this is again a real world data set. It is academic research papers with their authors and publications and whatnot. So that's a big graph. It's 2.6 billion nodes, almost 9 billion edges. And as I said, that's not by any means the biggest graph that we have worked with. So there's plenty of other resources that you can kind of refer to. Sure, I think if you have any particular comments here.
No, yeah, we have documented and uploaded examples of all the features that we saw in the slide deck and some of the features that Arvind also showed in the demos, like shortest path or polymorphism using derived tables or views and edge constraints. All of them are samples are documented. So please go and take a look and let us know if you have any questions.
Sounds good. Thank you, and thanks for the questions. I think there was, with this platform, I think it's pretty good to see those Q&A going back and forth. Thanks, Kevin, for facilitating that.
Yeah.
If there's any trailing questions you have for us, I think we can take those. Otherwise, I guess it's a wrap.
Yeah, got one question here about whether you've seen the network database model from the past. So the pre-relational network model.
Sure. I don't have any particular comments on it, but Shreya, I don't know if you've.
Yeah, no comments to add for that. I mean,
all I can say is this. I mean, you looked at those few, the sample queries that we had from the social network benchmark, the LDBC one. I did the T-SQL implementations pretty much, from scratch, and then I was like wondering, this query looks a little big. And then I happened to pull out, if you go to the LDBC GitHub, they have a reference implementation for one of our competitor products, which I will not name here, but most of you probably will know what I mean. And you take that language and you put the T-SQL against it, it's fairly similar if you actually look at, of course, there's syntactical differences and so on. So I do think that we have a very easy to implement and understand solution, which is very capable as well. Of course, there will be always incremental demands for functionality and integration with visualizations and so on. We will keep reviewing and addressing those. I think SQL Graph is here to stay, and we want more of you to explore and use it in your applications. And we will support you in the product by enhancing it as much as we can. All right.
All right, that sounds good. Thank you so much. And thank you, everybody who attended tonight. Come back with us Monday. We'll have Shop Talk. Tuesday, we'll have our main meeting. Both of those will be up on meetup.com/TriPass sometime pretty soon. Until then, thank you again for tonight, Arvind and Shreya. We appreciate the presentation. I got some kind words in chat for both of you as well.
Thank you.
Thanks for having us.
Thanks for the opportunity. Yeah.
All right.
Exactly.
Everybody take care now.
Same to you.
Bye.
Bye-bye.
Take care.